Hey, welcome everybody. So today we're going to be talking about pH and pOH. And so by the end of this video, you guys should understand what they are and how they're calculated. So first up, what is pH? So pH actually has a meaning. It is the power of hydrogen. And we use that power not to mean how powerful it is, but literally, mathematically, the power. pH is related to the exponent that is on the concentration of hydrogen, which, by the way, is the same thing as the concentration of hydronium, right? One of them includes the water molecule and one of them doesn't, but they both represent extra hydrogen present in a solution. The calculation of pH is very simple. In fact, the calculation of P anything is very simple. Anytime you see that P, meaning power for something, we are using a logarithm. So the function for pH, pH is equal to negative log of the hydronium concentration or hydrogen ion concentration. So that's it. You just put negative log and then the concentration of the hydronium, and then that gives you your pH. Similarly, pOH is the power of hydroxide. pOH, again, is related to the exponent, which is the power, right, of the hydroxide ion concentration. And it is calculated very similarly to pH. It is the negative logarithm of the hydroxide ion concentration. All right, so then why would we use pH and why would we use pOH? So pH is actually more commonly used. On the pH scale, you have 14 at the top, you have 0 at the bottom. So all of your values for pH should be between 0 and 14. 7 is right in the middle, and 7 is going to be neutral. So if something has a concentration to the power of -7, it is going to be very close to neutral if it's not neutral. Anything above 7 is going to be basic on the pH scale, and anything below 7 is going to be acidic on the pH scale. Why? Because if it has an exponent of times 10 to the -1, and we do a negative logarithm, its pH is going to end up being close to 1. If it has an exponent times 10 to the -13th, which is very, very small, then it's not very acidic at all. And when you do the negative logarithm of that value, it's going to come out closer to 14, and it's going to be basic. So because the exponent on your hydrogen ion concentration is related to the pH, the scale kind of works almost backwards of the way you think it would. Okay, high numbers on the pH scale don't mean a lot of acid. High numbers on the pH scale actually mean that it's more basic. It's the lower values, the values less than 7, that means that it's an acidic substance. The pOH scale, since it's calculated with hydroxide instead, it works the opposite way. I mean, it's still a scale from 14 to 0. So all of your values for pOH should be between 14 and 0. And right in the middle, 7 is still going to be neutral. But because we're basing this calculation on hydroxide as opposed to hydrogen, the top of the pOH scale means that it's acidic. So anything above 7 is going to be acidic, and anything below 7 is going to be basic. Now, when you have a hydroxide ion concentration and you negative log that, you get pOH. Okay? So we can use pOH when we have basic solutions, and we can calculate pH when we have acidic solutions. But what if I have a basic solution and I want to know the pH? Well, there is a relationship between the two. So the relationship starts off with a familiar equation. So we know that Kw is equal to the product of our hydrogen or hydronium concentration and hydroxide concentration. And so if I negative log that, then I would have to negative log both sides, and so that would be the negative log of hydrogen times hydroxide. And the way that logs work, if I do that, then really what I end up doing is negative logging each of those individually and then adding them together. So it'd be the negative log of the hydrogen concentration plus the negative log of the hydroxide concentration. And so really all of this is just the kind of long-winded way to derive this function. So we know that Kw is 1 times 10 to the -14th power. If I negative log that, I get 14. So the negative logarithm of Kw should be 14. If I negative log the hydrogen concentration, that's pH. And so 14 is going to be the sum of my pH and my pOH. What does that mean? That means that if I know the pOH, if I have a basic solution, I take my hydroxide concentration, I negative log it, and I get a pOH, I can really rearrange this, and I can say that 14 minus that pOH will equal my pH. So this equation right here is important, and it allows us to go from talking about pOH to pH, no matter what concentration I started with. Okay, so here's an example where we can actually put that into action. It says to calculate the pH of a 15 molar solution of ammonia, the Kb for ammonia is 1.8 times 10 to the negative fifth. So step one, we have to figure out whether the substance we're given is going to form an acidic solution or a basic solution based on its formula. Ammonia is a base. Besides the fact that the formula doesn't start with hydrogen, and because we've commonly seen how it can act as a base, we were given a Kb for this one. And so when you're given a Kb, more likely than not, you're dealing with a base. So we are working with a base. Okay, so second thing, once you know you're working with a basic substance, you need to write the dissociation equation. For that base in water. And so for ammonia, if I put NH3 into water, and remember these are reversible reactions, then if the ammonia acts as a base, it's going to take a proton, so it's going to become NH4, and that proton comes from the water, so water's acting as an acid really by donating that proton to ammonia, and what I'm left with there is hydroxide. And so this would be the dissociation equation for this reaction. Okay, and I'm not quite sure why I don't have the rest of these notes written out, but whatever, we'll just go with it. Okay, so step number three, write the dissociation, the expression. So you're going to write that equation either for Ka or Kb. And for this case, because we're dealing with a basic substance, we would be writing the equation for Kb. And so the way that I would write that is, I'm just going to do it up here. Remember that it's an equilibrium expression really, right? And so it's going to be my products over my reactant. Remember that for Ka and Kb, we take out water. And so the way that this works is, we know that we're going to have the 15 molar here, and that we don't have any of this to start with. We know that we are going to lose on this side of the equation. We're going to lose reactant in order to produce these ions to produce products. And so for my equilibrium expression, what I'm going to do is set Kb equal to my products, which is x times x, otherwise known as x squared, over my starting concentration minus x. Now, if I look at Kb is 1.8 times 10 to the negative fifth. So remember the trick to this. If I multiply that times 100, it becomes 1.8 times 10 to the negative third, which is 0.0018. Compared to the molarity of the solution we're starting with, 15 molar, it's nowhere near 15 molar. 0.0018 would still be really, really small compared to my starting molarity. In fact, if I subtract it and then round my molarity back to 3 significant figures, it's not even going to make a dent. So honestly, we can ignore x in this case on the reactant side. And so when I write my expression for Kb, right, my Kb is equal to hydroxide times NH4, plus over NH3, it becomes x squared over 15.0. And then Kb was a value that we were given, and so I can go ahead and substitute that in here. Kb is going to be equal to 1.8 times 10 to the negative fifth. So I have 1.8 times 10 to the negative fifth is equal to x squared over 15. Okay? So then, after we have written our dissociation expression and we have filled it in with the available data, we actually need to go ahead and solve for x. Okay, now this is really, really important to keep in mind, and I think this is something that is throwing kids off. If you had Ka, then X is going to be your hydrogen or hydronium ion concentration. If you were solving using Kb, then X is equal to a hydroxide ion concentration. And that's what we're doing in this case. In this case, when we solve for X, since we're starting off with Kb, then X is going to represent a hydroxide ion concentration. So I can go ahead and actually solve this problem. So I'm going to first multiply 1.8 times 10 to the negative fifth times 15. And so I end up with 2.7 times 10 to the negative fourth is equal to x squared. So then I can simply take the square root of that. And I end up with x is equal to 0.016 as my molarity. And again, since this is a Kb expression, since we're dealing with a base here, then that is equal to the hydroxide ion concentration. But the question was really asking for the pH. So here's what we can do in this case. Since what I have is a hydroxide ion concentration, I can go ahead and negative log this. And so if I do negative log of 0.016, that's going to give me my pOH. So negative log that answer, I get 1.78. Okay, so my pOH is 1.78, but I was not asked to find the pH. Again, we can use that relationship between those two. We can say that 14 minus the pOH is going to give me the pH of this solution. So 14 minus 1.78 gives me 12.22. So therefore, my pH is equal to 12.22. So that would be the pH of this solution. So make sure that you are calculating the right thing. Again, if you are using a Ka expression, then when you write that expression, one of your ions is H3O plus or H plus. And so when you find X, you are finding the H plus concentration. And when you negative log it, you are finding pH. If you're setting up a Kb expression and one of your ions is the hydroxide ion, then when you find X, that is equal to the hydroxide concentration. And when you negative log it, you're finding pOH. And there's kind of a quick and easy way that we can organize these functions here. And so this is just kind of a way for you guys to figure out sort of how to convert between pH, pOH, H plus, and OH minus concentrations. So I'm actually going to write these in different corners underneath. So this is just kind of like a little reference. pH in this corner, pOH in the other corner. And then down below, I'm going to put H plus, and I'm going to put OH minus in the other corner underneath pOH. Why am I doing that? Just because we can kind of talk about how you go back and forth between things. So if I have my H plus concentration and I want to convert that to a pH, then the formula that we learned was to take that H plus concentration and do a negative logarithm to it. If I have a pH, I can actually go backwards because the opposite of a logarithm is base 10. So if I have the pH and I want to convert that back to a concentration of hydrogen or hydronium, then I can actually use base 10. So I would do base 10 negative and then put the pH value in. And that would take my pH and turn it back into a concentration. We know that if we have the pH and we want to calculate the pOH, we can actually do 14 minus the pH will give us the pOH. And if we want to go the opposite way, we can kind of sort of do the same thing. It'll be 14 minus the pOH this time, that'll give us the pH. If we want to go from hydroxide ion concentration to pOH, again, we would do the negative logarithm of that concentration. And if we want to go backwards, the opposite of log is base 10. So it would be base 10 negative pOH. And that would turn my pOH back into a hydroxide ion concentration. We can even go back and forth between hydrogen and hydroxide ion concentrations using kW. So if I have the hydrogen concentration and I want to get the hydroxide concentration, what I can do is I can take kW, divide it by my hydrogen concentration, and that'll give me the concentration of hydroxide. Works the same way if I go the opposite direction, but this time I would take kW and divide it by the hydroxide ion concentration to get my hydrogen ion concentration. So you can use these to kind of figure out how to go from one to the other. And the problem we just did, the first thing we did was we set up that expression for Kb, we solved for X, and X represented our hydroxide ion concentration. So I was right here. The first thing I did was negative log that to get pOH, and then I subtracted from 14 to get to pH. So you can actually go from one spot to another using this chart and figure out what calculations you have to do to get from the concentration you have to the value you want. Hope this helps.